All right, so we are on our second day of 6-2. So now we're talking about dividing with simplifying our radicals, and then also rationalizing comes with dividing. Yesterday, I was talking about how I like to make little lists of my perfect cubes, perfect fourths, perfect fifths, kind of at the top of my paper. So today I'll give you a chance. You could write these out if you want. Usually I have the kids just kind of write it out and do it in their calculator, and then we move on. But so this means 1 squared, 2 squared is 4, 3 squared, 9, 4 squared, 16, 25, 36, 49, 64, 81, 100. Now next I'm looking at perfect cubes. So 1 cubed, 1, 8, 27, 64, 125, 216, 343, 512, 729, and 1000. Okay, then I'm looking at perfect fourths. So 1, 16, 81, 256, 625, 1296, 2401, 4096, 6561, and 10,000. And then perfect fifths, 1, 32, 243, 1024, 3125, 7,776, 16,807, 32,768, 59,049, 100,000. All right, so usually just have the kids put those in the calculators, and we just kind of look at these numbers and just kind of, by no means do you have to memorize any of these things. If you've got a calculator in front of you, you can figure out what is a perfect square, what is a perfect cube, and fourth and fifth. If you don't understand what a perfect cube and fourth is, then a calculator won't help you, okay? But as you'll start to practice these problems, a lot of times I really only need to be familiar with, one we don't even use. Like those two, when you're in perfect fifths, we don't usually have ones that go to 16,000. Okay, when I'm in perfect fourths, usually I'm just dealing with about the first 4. And then in cube roots, typically most of them are there. And then perfect squares, well, they kind of almost go all the way down and even further. Okay, so that's what I was talking about yesterday. Perfect squares are actually a little bit more difficult because there's a lot more numbers that are going to show up as perfect squares that you'll need to test out and divide for simplifying. When you get to cube roots, fourth roots, and fifth roots, you have a lot less options. Okay, so make sure when you're checking to see if a number divides into what's under your radical, you are only checking these numbers. Okay, otherwise you are wasting your time, and you don't want to waste your time. Okay, so you can use this. So students usually like to kind of write those down, and they kind of flip back and forth with this. I won't let you use this on your test or your quiz. I'll just tell them you can recreate and write those things down, because I want you to know how did you get those, and you're not just copying something from a list you made days ago. I want you to understand, how did we come up with those numbers? Okay, because then I truly understand what a perfect fifth, fourth, cube root things are. Okay. So with dividing radicals, same rules as multiplying. You can only divide radicals if they have the same root or index. So those would be the same numbers. So I can either write it as 2 separate radicals or one fraction within that same index. Okay, and there'll be times when one way will be better than the other. So we are going to simplify. Now with number 1, there's 2 ways you can write it. We can write it as 1 square root or a separate square root. Now, why do you want it as 1 square root would be if I can divide 36 and 25. I cannot divide them evenly without getting decimals, so this form is not helpful. It's actually more helpful in the form that it's in. because the square root of 36 is 6. The square root of 25 is 5. So when they're separate, I think of them as separate things I'm taking the square root of. And now that's my final answer. Okay, with number 2, we're jumping into cube roots. So when I look at 162, if I look at my list up there, 162 is not a perfect cube, neither is 3. So the form that it's in right now might not be helpful. Let's try the other form. They're both cube roots. Let's make one giant cube root and see if we can simplify that fraction and then take the cube root. So what I find out is that 162 divided by 3 is 54. And then when I'm dividing exponents with the same base of x, I can subtract 5 and 2, so I get x to the third. Okay, so when I made it one fraction, I was able to simplify it, so there's no longer a fraction left inside. Now we're just doing what we did yesterday, and I'm looking for, well, what perfect cube would divide 54? So I take a look at my perfect cube list. 8, 27, those are the only things I'm going to try because 64 is too big. Okay, so what divides 54 would be 27, and it goes in how many times? Twice. Okay, so the cube root of 27 is 3. That comes out. This 2 stays in. I made that really far apart. And then, oh, because I need the x. That's why I did that. The cube root of x to the third would be x. I'm going to stretch that out so it doesn't look like that. Index of 3 is on the x. Okay, notice again, my directions are assume all variables are positive, so we don't need to worry about absolute values today. Let's hop to the next one. Same thing with 4. Now I'm dealing with perfect fourths. So 1024, is that a perfect fourth? It is not. Okay, neither is 4. So let's go try our trick that we did last time. And let's make this one fraction and simplify within the fraction first, because typically that is going to make it much easier. So I'm going to divide inside of there. Remember when you are dividing and you're simplifying that fraction, it's still under the fourth root. You have not taken the fourth root, so you can't take that radical away. I will see students divide, and then like on the last problem, they'll say the answer is 54x to the third because they divided them, and then they think the radical's gone or something. I don't know. Okay, so when I take 1024 divided by 4, I get 256. And then I subtract those exponents. So I'm taking 15 minus 1 gives me the x to the 14th power. Okay, and then if I do look, 256 is a perfect fourth because 4 to the 4th power gives you 256. So that means the 4th root of 256 is 4. That will come out. And now I need to still simplify x to the 14th. That power is larger than 4, so I will be able to break this up. So like I talked about yesterday, a few different ways you can do it. The least amount of steps is to find the largest power on x that 4 can divide, but is smaller than 14. What's remaining would be 2, because remember when you multiply the exponents together, or you're multiplying these powers together, you add their exponents. So 12 and 2 would make 14. Okay, so the 4th root of x to the 12th would be x to the 3rd. That comes out with the 4. And then you have 4x to the 2nd remaining inside the radical. The other option I talked about with breaking up x to the 14th, you can write out your x to the 4th, but how many times did you have to write out x to the 4th? You could write it out 3 times, and then there'd still be 2 remaining. So this would give me x times x times x times the 4th root of x to the 2nd. Your x times x times x is where that x to the 3rd comes from. Okay, you can also kind of start to think of this as we talked about with division before. How many times does 4 go into 14? It goes in 3 times evenly with 2 left over, is another way to kind of check your work. Okay. All right. So there are going to be some cases where if I don't have a radical on the top, I can't divide the 5 and the 2. I can't write that as a single radical. Okay. We are also not allowed to leave a radical symbol in the denominator. So then we must use something that's called rationalizing the denominator. So we didn't have to do any rationalizing in any of these because my denominator was a perfect square here. I could divide these two so that there wasn't a denominator, so I didn't have to worry about that. Same thing here, I could divide those two so there wasn't a denominator. I can't divide these two, and 2 is not a perfect square. So we practiced this already, where we had to multiply the denominator times itself to get a perfect square. Make sure you do not multiply that 5 times 2, because 5 is not in the square root. And then this would be the square root of 4. And that's what makes it no longer, that we will no longer have a radical in the bottom, because I can take the square root of 4 and get 2. Okay, that part should we review. Now number 2 is going to be more difficult because this is going to be applying what we did in number 1 to our algebra 1 review to a cube root idea. So this is written as 1 radical, but I can't simplify 5 divided by 4 without getting a decimal. So it's actually going to maybe be easier if we keep them separate, not because I can take the cube root of 4 or the cube root of 5, but then I'm focusing on I need to rationalize the denominator. So I'll have to multiply by a radical. It must be a cube root, because the only way you can multiply radicals is if they're the same index. So in this one, we had to use a square root. And this is where kids get really confused because they want to take it times itself, because that's what they've done all along whenever they've rationalized things, because 2 times 2 gives you 4, right? And 4 is a perfect square. But if you take something times itself, you are always going to get a perfect square. We are not taking something times itself to get a perfect cube. How many times do you have to take something times itself to get a cube? You have to take it times itself 3 times. Okay, so a few different ways to think of this. We could do, if I have 4, you can multiply it by 4 and 4. So you're multiplying, that would give you a perfect cube of 64. So you are multiplying 4 times 16. So I'm taking 4 times 4 squared to get 4 to the 3rd. That would be one way to think of it. You'll have to do some simplifying with that because you didn't find the smallest perfect cube. So if I go back to my list here, so we can use 64, but we'll have to do more work. 8 would be the smallest perfect cube. Because if I take 4 times 2, I get 8. And 8 is a perfect cube, so I'll be able to take the cube root, and then there would no longer be a radical. So this is going to be the least amount of work, if you multiply by the cube root of 2. So now I can multiply this 5 and 2 because they are both under a cube root. I'll put it over here. So I'll have the cube root of 10. In my denominator, I have the cube root of 8. That is a perfect cube. What is the cube root of 8? That is 2. That's how I no longer have a radical in the bottom. And then the cube root of 10 will stay because 8 can't divide it evenly. Okay, if we would have used 64, then I would have had to break 64 up using 8 as a perfect cube. So it would have taken us longer. Go ahead and try these next 3 on your own from everything we've talked about in this lesson. See if it's making sense. Pause the video and then come on back to check your answers. All right, with A, I'll need to multiply by the square root of 2 on the top and bottom to rationalize my denominator since I can't simplify it any other way first. So 2 times the square root of 14. The 7 and the 2 can multiply together since they're both in the radical. The 2 on the outside will stay on the outside. And then I'll have the square root of 4 in my denominator. What is the square root of 4? It is 2. Then I have 2 square roots of 14. If anything that is left outside of your radical can be simplified and divided, then you need to do so. So that would just give me 1. So my final answer is the square root of 14. So check that you got that. All right, hopefully that one was okay. Square roots are usually okay for a lot of students because that's review. One like part B and C, they struggle with a little bit more. So B, I cannot simplify anything the way it is right now. It doesn't help me to change it to this form because it can't be simplified in that form anyways. So I'll need to rationalize. Okay, rationalizing the denominator is probably your last resort. First, you're going to see, are they perfect cubes? Can I simplify it as is? Can I divide them? Those are the things you check first before you resort to rationalizing the denominator because it takes longer. Okay, all right. So I know I need to multiply by a cube root. I know I'm trying to get a perfect cube in the denominator. And so right now I have a 5. I got to think about what do I multiply 5 by so that I get a perfect cube. Okay, couple different ways you can think of it. I do not take 5 times 5. 5 times 5 is 25, which is a perfect square, not a perfect cube. 5 times 5 times 5 is 125. That is a perfect cube. So that's what I want. Because when I take the cube root of 125, I get 5. Okay, so that means I'm multiplying 5 by 25. So that's what I'm going to put in here. Okay, sometimes I'll tell students, well, think about that you're trying to get 5 to the third. So if I take 5 times 5 squared, I'll get 5 to the third. And then I can take the cube root of 5 to the third. So if that's helpful, you can think of it that way. Also, I have a y squared. So the same concept. Well, I got to multiply y squared by something to get a perfect cube. Y cubed would be a perfect cube. What would I multiply y squared by? I just need y to the first to get y to the third. So that's what I multiply by on the top and the bottom. So then I'll have the cube root of 175, all of x and y in there, over the cube root of 125 y cubed. Okay, remember the whole point of what we're doing is to get rid of the radical in the denominator. And so if I've done this correctly, 125, the cube root is 5. The cube root of y to the third is y. Okay, so I no longer have a cube root. If we did not multiply by y, I'd have a y squared, and y squared couldn't come out. So you'd still have a cube root of y squared in the bottom. Okay, so everything, whether it's a variable under there or a number, has to become a perfect cube. All right, then I need to double check. 175. If I didn't multiply by something to get the smallest perfect cube, I'm going to have to simplify the top. So in some cases, you might make that mistake. So you need to make sure you're double checking your perfect cubes of 8 does not divide 175, 27 does not, 125 does not. So we are done. Okay. And then C. 24 is not a perfect cube, 3 is not a perfect cube. before I start to rationalize, I should divide these, because I can. 24 divided by 3 is 8. X to the 13th over x to the 8th would be x to the 5th. Now there's no longer a denominator. I don't have to rationalize this problem. I put this problem on here last because a lot of students will go, all right, now I need to multiply by the cube root of 9x and the cube root of 9x. And they multiply that out. Now they got to simplify the top, simplify the bottom, divide things out. They create a problem that's going to take them twice as long. So like I said, always look for your perfect cubes first. See if you can divide next. If you can't, then you rationalize. Because the cube root of 8 is 2. I can break up x to the 5th into x to the 3rd times x squared. Cube root of x to the 3rd is x. Keep your x squared inside. That should be the same answer you get if you rationalize, but you will have a lot of simplifying to do. So if you tried that, make sure you've simplified everything and then you still get this answer. But divide first if you can. All right, that is our lesson. Tomorrow we will have our quiz. Please reach out if you have questions.